Conservation of mechanical energy. Basically, this lesson is that the total initial mechanical energy is equal to the total final mechanical energy. In other words, the total initial kinetic energy plus the total initial potential energies is equal to the total final kinetic energies plus the total final potential energies. So the initial kinetic energy, we only know of one type right now, and that's called translational kinetic energy. So the initial kinetic energy plus the initial gravitational potential energy plus the initial elastic potential energy is equal to the final kinetic energy plus the final gravitational potential energy plus the final elastic potential energy. That is 1/2 mv initial squared plus mgh initial plus 1/2 kx initial squared is equal to 1/2 mv final squared plus mgh final plus 1/2 kx final squared. So let's do an example. I have a red block at the top of an incline, and we're going to call that situation 1. And then the block is allowed to fall down or slide down the incline because of its own a component of its own weight. And it falls down the incline and then moves horizontally to the left until it comes in contact with the spring. And it compresses the spring until the system comes to a stop for a moment. And my question to you is, how much does the spring compress from its original position in situation 2? And we can kind of draw a diagram here with blue showing how much the spring compresses. And really, so I'm asking for this x value here. How much did the spring compress from its original position? Now in situation 1, this block starts off at some height above the ground. And so let's give some givens here. That height above the ground, let's say that's 5 meters. The spring constant of the spring, let's say that's 150 newtons per meter. So that's a pretty springy spring. The mass of the block is 5 kilograms. We know g is, or the acceleration due to gravity, is 9.8 meters per second squared. And lastly, I want to find what is the compression of the spring. Okay, so here's what we know. The total initial mechanical energy, or in this case, the mechanical energy in situation 1, is equal to the total mechanical energy in situation 2. All the total mechanical energies in 1 is we could have the translational kinetic energy in 1 plus the elastic potential energy in case 1 plus the gravitational potential energy in 1. That's equal to the total translational kinetic energy in 2 plus the elastic potential energy in 2 plus the gravitational potential energy in 2. Writing out the formulas, that's 1/2 mv sub 1 squared plus 1/2 kx sub 1 squared plus mgh sub 1. That's equal to 1/2 mv sub 2 squared plus 1/2 kx sub 2 squared plus mgh sub 2. Alright, now in case 1, the red block is at the top of the incline and it's before it's allowed to slide, so it has no velocity. So when I look at my first formula here, the 1/2 mv sub 1 squared, there is no v sub 1. V sub 1 is 0. 0 times anything is 0. This term drops out. In case 1, when we look at the next term for elastic potential energy, there's no spring involved in case 1. It's just the block at the top of the incline. So your x sub 1 is 0. So this whole term goes away. So the only term I'm interested in case 1 is gravitational potential energy. Now in case 2, the block has come to rest at the moment where the spring is compressed. So my V sub 2 is 0, and this whole term cancels. Now the spring has been compressed, so there is some elastic potential energy. So this term we're going to keep. In terms of gravitational potential energy, the block is moving along the ground, so there's no height above the ground. My H sub 2 value then is 0, and so this term drops out. So the equation that I'm left with is mgh sub 1 is equal to 1/2 k x sub 2 squared. The x sub 2 value is really what I'm looking for. So what I would like to do is rearrange this formula for the x sub 2 values. So I'm going to multiply both sides by 2. Then I'm going to divide both sides by k. And then I'm going to take the square root of both sides. And so I'm left with an expression for x sub 2, which will be 2 times the mass of the block multiplied by the acceleration due to gravity multiplied by the height in situation 1 divided by k, the spring constant. So let's go ahead and plug in the numbers. So x sub 2 is equal to 1.807 meters. Following our rules for significant figures, my smallest value has one significant figure, so technically we could write that out as 2 meters, rounded to 2 significant figures. Okay, another quick example is, let's say we have someone that jumps off a diving board, and when they reach their highest point in their trajectory before they hit the water, they're 3 meters above the water. We're going to call that the initial condition. The final condition is right when they hit the water and they're going their fastest. And the question is, what is the speed right when they hit the water? Here's what we know. We know the total mechanical energy in situation 1 is equal to the total mechanical energy in the final condition. So in the initial condition, the object or the person that's diving is actually at its highest point, so they're not moving. There's also no spring or elastic properties, so therefore there's no kinetic energy, there's no elastic potential energy, but there is gravitational potential energy. So in the initial case, all of the energy is gravitational potential energy. In the final case, if we make the water level the reference level, then all of the energy is kinetic, so kinetic energy final. And writing this out as a formula, this would be mgh sub I is equal to 1/2 mv final squared. And so rearranging this formula for v final, we will multiply both sides by 2. And also notice the masses cancel, which is really cool. And we multiply both sides by 2, I get 2gh sub I is equal to v sub final squared. Take the square root of both sides, and now you have an expression for v sub f, and v sub f therefore is equal to the square root of 2gh sub I. So how does conservation of mechanical energy apply to pendulums? Let's take a closer look. So with the pendulum, you have a mass hanging from a string that's attached to some fixed position, and your mass, which has a name called bob, the bob swings back and forth or to and fro. At the bottom of the swing, we say that bob, it has all kinetic energy. So it's moving its fastest, all the energy is energy of motion. At the very top of the swing, we say that bob stops for a moment so he could change direction and come back down. And so all of the energy in the mass of bob is gravitational potential energy. So at the bottom, it's all kinetic. At the top, it's all gravitational potential energy. This side also, on the left side, is also the top of the swing, so we all have or Bob has gravitational potential energy. Now what if we're right in the middle, for example? If we're right in the middle, we have a combination of gravitational potential energy plus kinetic energy, and that will give me, if I added those two values at that point, the total mechanical energy of the system. The total mechanical energy of the system is the same everywhere. So whatever that value would be right here, this total mechanical energy, that would be equal to the gravitational potential energy at the top, and that will also be equal to the kinetic energy at the bottom. Let's look at another typical example that we see when we're dealing with pendulums and conservation of mechanical energy. At the bottom of the swing here, again, if the pendulum is moving to and fro, all of the mechanical energy is kinetic. At the top of the swing, all of the energy is gravitational potential energy. Because of that, what we say is that there must be, for gravitational potential energy, there must be some height above a reference level, and that height is represented here in blue. If you notice here, I have just created a right triangle, which I'm going to outline in green. And this right triangle will have an angle. It's a right triangle. And based on this information, your task is to find H. What is H? And if you know H, then you should be able to find the gravitational potential energy of Bob at the top of the swing. Now, one of the things we know is there's a typical notation for the length of Bob from its fixed position. That's typically called a length of a lever arm, and that's from the fixed position to the center of Bob, and that's called L. If I know my angle, which let me write that again on red, if I know theta and I know L, can we find this side of the right triangle? And knowing trig, of course, we can. So let's do that real quick. My question mark, actually let's give it a different letter here. Let's call it, for lack of anything better, I'm just going to call it B. So B over L is going to be cosine theta, or B is going to be L cosine theta. If you look at the diagram, can you see then how you would find H? Let me point something else out to you. Let me see if I can fit this in here. Let me pick a different color. We'll go with purple. If you notice here, let's see, I'm going to try and fit this in. The length from here to the center of Bob. Let's see here. So in purple, this length here is also called L. So it's hard to tell from this picture, so I'm just going to go ahead and tell you here. But if you take the length of L and you subtract the length of B, you should get H. And L then, we know, let's say that's given, and B is just L cosine theta, and that will give me H. And then once I find H, then I can plug it in the equation mgh to find the gravitational potential energy at the top of the swing. Now, we can also look at law of conservation of mechanical energy when we're dealing with the spring example. And one of my favorite is when we're looking at a vertical hanging spring. And so let me go ahead and draw a diagram for you, and we'll talk about what's happening. So what we have here is basically four situations. In the first situation, we have a spring that's hanging vertically. There's nothing on the spring, it's just in its natural position. In the second case, there is a mass hung on the spring, and then the spring stretches a little bit. In the third case, we have something or someone pulling on the mass and stretching the spring even more. And then in the fourth case, now what has happened is whatever had pulled the spring and the mass down, they have let go, and now the spring has shot upward, compressed upward past its original position, and now it's oscillating back and forth. Okay, now when the spring is at its highest position and it's compressed, I'm going to call that situation 1. When the spring is at its original position and coming, say, down, and as it's oscillating, I'm going to call that 2, or coming back up. When the spring is at the position when it was at when we first hung the weight on it, we're going to call that 3. And when the spring is at the position where it was pulled down and it also has the weight on it, we're going to call that situation 4. And again, imagine the spring is oscillating back and forth, like so. So let me give you some givens. Here's what we know. Let's say the mass of the hanging mass on the spring is 100 grams. We will convert that to kilograms, so 0.100 kilograms. We know the acceleration due to gravity. Let's say when we hung the mass on the spring stretched 2 centimeters. Let's go ahead and make up positive plus y, and it stretched 2 centimeters. So we're going to write that right here, that my x2 was 2 centimeters. And we're going to say it's a negative 2 centimeters because it went down 2 centimeters. So my x sub 2 is a negative 0.02 meters. And let's also say when the spring goes all the way up, so it's compressed to its maximum point or at position 1, let's say that it compresses, we'll call that x sub 1, a positive 1 centimeter. So x sub 1 is a positive 0.01 meter. And here's what I want you to find. Find the total height above its reference level, which we'll call the reference level at 0.4. Why don't we call that total height h? Find that total height. Find the velocity at position 2 of Bob, or the Bob spring system. Find the velocity at 0.3 and find the total mechanical energy of the system. And let me just draw in for you what h is. H is that height right there. Okay, so using conservation of energy, I know that the total mechanical energy in case 1 is equal to the total mechanical energy in case 2 equal to the total mechanical energy in case 3, and that's equal to the total mechanical energy in case 4. So writing all of this out, we have a lot going on, but what you see here is the mechanical energy in case 1 is simply gravitational and elastic. The total mechanical energy in case 2 is gravitational and kinetic. The total energy in case 3 is a combination of all three, elastic, kinetic, gravitational potential. That's in case 3. In case 4, there's only one type when Bob is at its lowest position, and that's elastic potential energy. And notice that the stretch of the spring is the same value, that h value, when it's at the very, very top. So if you could find that total h value there, you could find the total mechanical energy. So we're going to move on from here. We'll be talking more about that later. All right, let's quickly look at conservation of mechanical energy with roller coasters. Let's call at the top here situation 1, in the loop 2, and when they've come out of the loop 3. If we were to draw a free body diagram in case 1, notice we would have two forces, the weight and the normal force like that. In case 3, again, we would have the weight down and the normal force up like that. In case 2, of course, we have the weight down, but we have another force, which is the normal force, and in this case, it is down. In case 2, notice that the car is going in circular motion, so the net force acting on this car, which is the weight plus the normal force, because they're in the same direction, is equal to the net force acting on an object when it's moving in a circle and that is called your centripetal force. Now, in case 1 with the roller coaster, if the car hasn't moved yet, all of the mechanical energy in case 1 is going to be gravitational potential energy in case 1. That's the total mechanical energy. In case 3, if the car is moving and it's at reference level, all of the energy is kinetic energy at case 3. So what's happening at case 2? Well, the cart is some height above the ground, but it's also moving. So in case 2, we have a combination of gravitational potential energy plus and kinetic energy. Conservation of mechanical energy says the total value in situation 1 is equal to the value at situation 2, and that's equal to the value in situation 3. Looking at a graph of just the kinetic energy as time goes on this roller coaster, basically what's happening is as time goes on, the kinetic energy is increasing. If you look at what's happening with the gravitational potential energy, in the beginning of the ride we have all gravitational potential energy, but as time goes on, it turns into all kinetic. But what about the total mechanical energy? What is that as the ride goes on? That stays the same throughout the whole ride. Lastly, I want to introduce to you the rate of power. Power is the work done divided by time, so how quickly was work done on an object, or it's equal to the energy transformed or the energy transferred over time. The unit of this power is in a joule per second, or it's in a watt. Now, because power is equal to work divided by time, and work is equal to force times distance over time, we can take distance divided by time and remember that that's average speed and say that that power is equal to force times your average speed. I'd like you to look at example 6-15 on page 159. Take a look at that example before you try the practice problems. I will give you a practice problem on power, and I think this example will be helpful in doing the practice problem. These practice questions are due at the beginning of the period on Monday, and keep in mind that we will go over, oh, I take that back, we have a holiday, so it's due beginning of the period on Tuesday. And we will go over these questions during the period. Have a great weekend.